Good morning, one and all. Uh, my name is Tamang, 21NS0-253, and I would like to introduce my topic, photoelectric effect. Before I start my topic, I would like to thank our HOD, Sir, Physics HOD at Sir, and our respected sir who gave an opportunity to talk on this topic, Sir C.B. Khatiwada, and my topic is photoelectric effect. As we all know and familiar with this topic. So now I'm going to discuss on the topic photoelectric effect. So my topic is photoelectric effect. So here we go. Introduction be like photoelectric effect is the process of emitting the electrons from the metal surface. When the metal surface is exposed to an electromagnetic radiation of sufficiently high frequency, for example, ultraviolet light is required in the case of ejection of electrons from an alkali metal. Or in simple word, it is a phenomenon in which electrically charged particles are released from or within a material when it absorbs electromagnetic radiations. Photoelectric effect is widely studied in the fields of quantum chemistry, condensed matter physics, and solid-state chemistry because it helps draw inference on the properties of solids and the properties of atoms and molecules. If we talk about the history of photoelectric effect during 19th century, in 1839 Alexander Imond discovered the photovoltaic effect while studying the effect of light on photovoltaic cells. Though not equivalent to the photoelectric effect, his work on photovoltaics was instrumental in showing a strong relationship between the light and electronic properties of materials. In 1873, Wellington Smith discovered photoconductivity in selenium while testing the metal for its high resistance properties in conjunction with involving submarine telegraph cables. During the 19th century only, after Alexander and Smith, scientists named Johann Elster and Hans Zettel, students of Heidelberg, investigated the effects produced by light and electrified bodies and developed the first practical photoelectric cells that could be used to measure the intensity of light. They arranged metals in such a manner with respect to their power of discharging negativity electricity, such as rubidium, potassium, alloy potassium, sodium, lithium, magnesium, selenium, and zinc for copper, platinum, lead, iron, cadmium, carbon, and mercury. The effects with ordinary light were too small to be measurable. The order of the metals for his effect was the same as in voltage series photoconduct electricity, the most electropositive metals giving the largest photoelectric effect. During the 20th century, in 1905, Sir Albert Einstein published a paper advising the hypothesis that light energy is carried in discrete quantized packets to explain experimental data from the photoelectric effect. Einstein theorized that the energy in each quantum of light was equal to the frequency of light multiplied by a constant. Later on, that constant is called Planck's constant. A photon above a threshold frequency has the required energy to eject a single electron, creating observed effect. Einstein was awarded the 1921 Nobel Prize in Physics for his discovery of the law of photoelectric effect. So here we know law of photoelectric effect emission. There is no time lag between the irradiation of the surface and ejection of the electrons. At a particular fixed frequency of incident radiation, the rate of the emission of photoelectrons, that is photocurrent, increases with increase in the intensity of the incident light. Photoelectric effect does not occur at the frequency less than threshold frequency. At the frequency above the threshold frequency, the kinetic energy of ejected electrons depends only on the frequency of the exposed radiation and not on its intensity. Here in diagram, we are simply explained the effect of photoelectric. This is a metal surface where the radiation or the light is striking on the metal surface, and after that the electrons a packet of electrons are ejecting from the metal surface. Principle. To understand the principle of photoelectron effect, the photoelectron effect must be applied. The photoelectric effect states that electrons can be pushed off the surface of solid by electromagnetic radiation. The ejected electrons are called photoelectrons, originally known as the Hertz effect because the photoelectric effect was first observed by Heinrich Hertz in 1887. When Hertz noticed that sparks would more readily jump between two charged surfaces that were illuminated with light. Hertz's observation would ultimately lead to Einstein's photoelectric law. The kinetic energy of an emitted photoelectron is given by E suffix k equals to hb minus E suffix I, where h is Planck's constant, v is frequency of the ionizing light, and ei is the ionization energy, which is synonyms of electron binding energy of the electron. The term photoelectric effect is only considered when discussing solids and exclusively. The process of photoionization follows a three-step model. The three-step model breaks down the process of photoionization into the independent steps. Number 1, the molecule will absorb the photon, causing the energy of the photon to be transferred to the molecule's electrons, which will become excited. Number 2, the excited electron will travel to the surface of the molecule. During this step, the excited electron travels, it may or may not collide with other particles. Any excited electrons which do collide with a particle will lose energy. Number 3, the excited electron will escape the surface of the molecule into the vacuum where it will be detected. Theory about the photoelectric effect. Number 1, the photoelectric effect cannot be explained on the basis of electromagnetic theory. Number 2, in 1905, Sir Einstein proposed that the photoelectric effect could be understood through the idea proposed by the German theoretical physicist Max Planck in 2000. Number 3, Planck was seeking to explain the characteristics of the radiation emitted by hot bodies. Number 4, Planck assumed that while the radiation is emitted continuously as little bursts of energy called quanta, but propagated continuously in space as electromagnetic waves. Number 5, Einstein proposed that light not only was emitted as quanta at a time, but also propagated as individual quanta, sufficiently small to be absorbed by the electron. Number 6, Planck found that the quality associated with a particular frequency V of light all had the same energy and that this energy was proportional to V, that is E equals to h nu. Number 7, photoelectric effect can be explained by the following equation: E equals to hv equals to h into V naught plus Tmax, where E is the total energy of the photon incident on the metallic surface, V is the frequency of the incident radiation, V naught is the threshold frequency of the metal, and T suffix max is the maximum kinetic energy with which the electron moves after ejection from the surface. If the frequency of the incident radiation is fixed, Tmax will not change. Hence, the stopping potential will remain the same even if the intensity is increased or decreased. If the intensity of radiation is increased, keeping the frequency fixed, the number of photons per second will increase, leading to more collisions per second and transfer of photon energy to more electrons. Thus, the number of electrons coming out per second will increase, leading to increase in photocurrent. Merits of photoelectric effect. It senses all kinds of materials, it has longer life, it has long sensing range and very reliable. It has very fast response time. It is less costly. Diffuse photoelectric sensor detects small objects including color mark and label detection. Photoelectric or retroreflective type can detect transparent objects. Through beam type can detect long range and it is tolerant of dirty environment. Minutes of photoelectric effect. Over course of time, lenses get contaminated. Its sensing range is affected due to color and reflectivity of the target. So beam type requires transmitter Tx and receiver Rx at two separate locations. Retroreflective type requires reflector in addition to Tx by Rx. This makes system installation complex. Derivation and calculation. Einstein photoelectric equation. If a photon incident with a frequency greater than threshold frequency, then energy of photon is given by E equals to hb, equation number 1, where h equals to Planck's constant. Now hb equals to phi naught plus k max, equation 2, where phi naught equals to work function, phi naught equals to hb naught, equation number 3. Now hb equals to hb naught plus ke max, ke max equals to hb minus hb naught, k into e suffix max equals to h bracket open b minus b naught bracket close, where b naught equals to threshold frequency and b is greater than threshold frequency. Let's see some examples relating the equation. Here the question is, a radiation of wavelength 300 nanometer is incident on a silver surface. Will photoelectrons be absorbed? So energy of the incident photon is E equals to hb equals to hc by lambda, E equals to hc by lambda e. Substituting the known values, we get E equals to 6.626 into 10 to the power minus 34 into 3 into 10 to the power 8 by 300 into 10 to the power minus 9 into 1.6 into 10 to the power minus 19, where E equals to 4.14 eV. The work function of silver equals to 4.7 eV. Since the energy of the incident photon is less than the work function of silver, photoelectrons are not absorbed in this case. Application of photoelectric effect. Number 1. Photocell. It is the most important application. It is most commonly found in solar panels. It works on the basic principle of the light striking the cathode, which causes the emission of photoelectrons, which in turn produces field current. A photocell is a resistor that changes resistance depending on the amount of light incident on it. A photocell operates on semiconductor photoconductivity. The energy of photons hitting the semiconductor frees electrons to flow, decreasing the resistance. Photocells are electronic devices which can be used to manage indoor and outdoor lighting. Photocell consists of an evacuated glass tube containing two electrodes, emitter C and collector A. Other example of photoelectric effect is photomultiplier tube. These tubes make use of photoelectric effect to convert light intensity into electrical currents. Number 3. Photocopier. We are mostly familiar with photocopier. It is also called copier or copy machine and formerly Xerox machine. A photocopier is a machine that makes copies of documents and other visual images onto paper or plastic film quickly and cheaply. Most modern photocopiers use a technology called xerography, a dry process that uses electrostatic changes on a light sensitive photoreceptor to first attract and then transfer toner particles or a powder onto paper in the form of an images. The toner is then first fused onto the paper using heat, pressure, or a combination of both. Copiers can also use other technologies such as inkjet, but xerography is standard for office copying. It is widely used in the business, education, and government sectors. Results and conclusion. As a result, the kinetic energy of photoelectrons increases with light frequency. Electric current remains constant as light frequency increases. Electric current increases with light amplitude. The kinetic energy of photoelectrons remains constant as light amplitude increases. So my colleagues, I would like to end up my topic here only. Thanking you all.